So it's a great pleasure to have Kana. His name is long, no? Kannabiran Seshasayanan. So Kana did his BTech from IIT Madras, which is like another IIT for people like David to know. But in India, people know IIT Madras. In fact, yeah. So he did his BTech. Then he went to ENS Paris for his PhD with Alexakis. After that, he did his postdoc in Saclay, and after that, he's moved to IIT Kharagpur as a faculty. He's a professor in IIT Kharagpur. So today he will talk on mean flow instabilities on surface gravity waves in rotating frame. Okay, Kana, please go ahead. You can start your talk.
Thank you, NKV. Yeah, thanks. So hello everyone. So I'll be talking about mean flow instability of surface gravity waves in a rotating frame, and we call this the Ekman-Stokes instability. So this was a work which I did when I was doing my postdoc in CEA Saclay, along with Basil Gallet, who was my postdoc mentor. So a bit of introduction on why we study surface gravity waves. So we know in the ocean you have all kinds of waves. In the ocean, internal waves, surface waves. So surface gravity waves are a very important component of the ocean dynamics, where, for example, if you take swell waves, you have this surface gravity waves which are generated by storms and wind in some very highly windy activity, let's say in the south of or near the Antarctic continent. You have a lot of wind and storms which generate a lot of perturbations in the system, and this highly agitated sea will send out waves across the ocean, and as they disperse, as they travel along, they become these nice swell waves, where you have this long wavelength gravity waves that propagate towards the coast of continents. And as they approach the coast, they start to break, or they start to increase in amplitude, increase in height, and it is at these places that they are used for surfing and other recreational activities. So surface gravity waves are also important for many other processes. For example, mixing of upper ocean. You have chemical exchanges with the atmosphere. Whenever you have a wave that breaks, it takes some part of the atmospheric air particles into the sea, and you have some exchange of some liquid also with the atmosphere, some chemicals with the atmosphere. So later, McWilliams had shown that, okay, say some internet connection is not good, but I hope it's fine. So McWilliams later on showed that it plays an important energy contribution to the global oceanic circulation. And recently, people are also very much interested in knowing how much transport do these surface gravity waves do. For example, when you have plastic and debris and oil that are spilled on top of oceans, and many people say that the surface waves also transport these debris that are on the ocean, and we should take into account the transport properties of these surface gravity waves. Okay, so surface waves not just interact by themselves, they also interact with the underlying flow. So for example, so we know that waves can also interact with an underlying mean flow. So for example, they can induce, they can distort surface currents. And one visual example of such an interaction are these Laminar circulations. So whenever you have waves on top of some background current, you can start to have these cellular structures that are formed, which are oriented along the direction of propagation of these waves. And it has some very important properties. It's very important for mixing of nutrients in the upper ocean. And an explanation for such a Laminar cell, generation of this Laminar cell, was first proposed by Craig and Lebowitz in 1967, where they wrote a couple an equation for the mean flow, which was driven by this wave and the background current, and they showed the formation of this nice Laminar cells. So we know that surface waves are actually propagating on the surface of the Earth, and we know that Earth is rotating. So what do we know about the effect of rotation on these surface waves? So firstly, we can say certain properties, certain things very clearly. The first thing is that it does not modify the dispersion relation of gravity waves in the ocean.
And that is just because the frequency of these waves, the frequency of the surface waves, is actually much, much larger than the frequency of rotation of the planet. So we do not expect any modification of the dispersion relation per se by the rotation on the gravity waves. But later, like for example, Ursel argued in 1950 that the rotation might play an important role in the mean Eulerian component in the mean flow. He argued that rotation actually induces a mean Eulerian flow which counters the Stokes drift. So I'll explain what is Stokes drift. Of a propagating surface gravity wave. On an average, you have some kind of a drift associated with this wave, and this drift is associated. It's called the Lagrangian velocity field. So the Eulerian velocity field, if you take any point on the velocity at any point on the field just oscillates up and down. But if you put a particles, because I'll show you later on a visual example that you have this drift that is induced, and that is called Stokes drift. And Ursel argued that you have a mean Eulerian flow which actually counters the Stokes drift. And the argument for this particular generation of Stokes, this anti-Stokes flow, which people call, can be seen below. So what Ursel did was to write an equation for the mean flow, which again I will talk about in a bit. If you write an equation for the mean flow, which Craig and Lebowitz showed early on, if you write an equation which Craig and Lebowitz showed later on, so if you write this equation for the mean flow, you have this equation, which is the evolution equation of the velocity field of the mean flow plus the Coriolis force, where you have this Lagrangian velocity, not just the mean flow velocity field, but you also have the Stokes drift. And what Ursel argued is that in this at steady state, you basically get um equal to minus us, and you get a mean flow which is opposite to the Stokes drift. So this is the so basically to conclude, you just say that rotation does not affect the dispersion relation of gravity waves, but it does induce a mean flow which basically counters the Stokes drift associated with the propagating wave field. And this was his argument, which seemed fine at that moment. And but we actually went back to this problem and we looked at it more clearly. And firstly, we wanted to understand what does it like. How does the dissipation of the swell waves? How does it scale with the properties of the flow? So, for example, many people have found that the dissipation of swell waves is not fully understood. It cannot be just given by pure viscous dissipation, and it is sometimes it can be an order of magnitude higher than just pure viscous effects. So, for example, Fabrice Ardouin, like he says that there's possible interactions with atmosphere, wind, and other sources that might explain the dissipation of swell waves. So, for example, if when you take satellite data of swell waves propagating on the ocean, and then you just track the height of the wave as a function of distance, you just put a simple fit with viscosity, and then you say, okay, this should be the dissipation rate. But what people found was that it's much higher, and the question is, like how are the waves getting dissipated? And secondly, we again wanted to look at this problem because of the importance of this particle transport by the surface gravity waves. So surface gravity waves in a rotating frame, as shown by Ursel, predicts a zero surface drift because it induces a mean flow which is opposite to the Stokes drift. So people said, at least it was under common belief, that surface gravity waves in a rotating frame do not transport any particles. Okay, so yeah, if you have any questions, you can stop me. So just to put it more clearly, so we look at the problem of waves in a rotating frame, and we look at the problem of what is the mean flow that is inducing. So it's similar to what Ursel asked, but we will be asking the same questions, like how much. We'll ask some more questions than what he asked. Like we also ask how much does the mean flow dissipate. So if the mean flow dissipates so much, we can say that the mean flow actually extracts energy from the surface gravity waves, and this would be an added dissipation on the surface gravity wave. So first question is, how much does the mean flow dissipate? And second question is, can this mean flow become turbulent? So if the mean flow becomes turbulent, it kind of means that you have nice waves which are propagating on top of the ocean, but the underlying flow is like actually much turbulent, and maybe this turbulent mean flow might be extracting a lot of energy from this from the surface gravity wave. And the third question that we wanted to and understand is how much particle transport is done by this mean flow. So you have a surface waves by itself does not transport any, in a rotating frame, we just said that it does not transport any particle. So we just wanted to like go back and look at it and see if there's anything different we find. So these are the questions that we'll try to answer. And our setup of this problem is a very simple setup. We just take propagating monochromatic waves. So just think about swell waves which are propagating from one part of the ocean to the other part, and then we have a system that is in rotating frame. So we don't take any beta plane effect. We take the simplest case. We just take rotation to be along the z direction, and there's no other component of the rotation vector. And we also take that the small slope limit. So basically, these waves are not breaking; they are not close to. They don't have any bottom boundary effect, and there's no overturning and stuff. So these are nice linear waves that we are considering, and we also do not consider any topography in the bottom. So it's just deep water waves. So what it means is that a typical vertical length scale is at least of the order of the wavelength of the system. So the wavelength is the wavelength of the surface waves, and if your depth is a few times the surface, the wavelength of the surface waves, we call it a deep water limit. So we just say that there's no bottom boundary effect. So this is a setup of the problem. These are some simplifications that we took. So in order to analyze this problem, and most of them are very well valid in the oceanic limit. If you take swell waves, they are like more or less in this setup. So on the right, I have this small nice sketch where I show these waves which are propagating to the right. So these are my axis, x, y, z. My rotation is along the z direction. And here the US is basically the Stokes drift velocity field, which has this particular profile, which is along the direction of propagation of this of the waves. So you have a drift associated with this wave field, which basically is given by this profile US.
Just one question. What is the K for the variation of the UZ?
Yeah.
Roughly,
So I'm coming. Yeah, I'm
what
just
is
coming. Yeah.
can
So,
you,
US. Yeah, thanks for the question. Sorry, I should have mentioned it here also. So, US is the velocity field associated with the Stokes drift, and this capital US is the amplitude times e to the power 2 kz, and k is the wave number of the waves. So, it's just 2 pi by lambda. So here, when I say small slope limit, a is the amplitude of this wave, and k is the wavelength and the wave number. Sorry. So it's 2 pi by lambda times a should be very much less than 1. So this is a small slope limit. The slope of the wave is very small compared to 1. And here, the typical vertical variation of this Stokes drift is also given by lambda. So the typical length scale is 4 pi, 2k is just 4 pi by lambda times z. So typical length scale is lambda over 4 pi. So
in real flow, what is the height where for US?
so
Variation is like 1 meter
yeah,
or 1 kilometer.
yeah. For example, in ocean swell waves, yeah, that's a good question. So in oceanic swell waves, for example, you have waves of the order of few tens of meters to hundreds, and about like can go up to a few hundred meters in terms of wavelengths, and you can have heights which are from a meter to about 10 meters.
Okay.
And the typical velocity of the Stokes drift might vary from few tens of centimeters, from few centimeters to few tens of centimeters, and in terms of a slightly larger amplitude, it can even go up to a meter per second. So these are like very large waves. So you have a whole range of waves that you can. We will discuss the oceanic limit later on, but these are the typical values that one would see in the ocean or observe in the ocean. Okay, so this is the setup of the problem, and to understand this problem, we use this wave plus mean flow description. So meaning we have an imposed system which is only has waves. So we consider waves at the dominant order, which is given by this ak, the slope of this wave. So for us, we have only waves that are propagating, and the mean flow is induced by these waves. So this mean flow which is being induced is actually, we take that it's too weak to modify these waves, and this can be asymptotically shown that if AK is a small parameter, the mean flow is actually the retroaction of the mean flow on top of this wave is actually small, that we can modify it. So it's of the order of AK. So if the effect is of the order, it's at the lower order of AK, so you can neglect the effect of mean flow on the waves. And so
by mean flow, you mean the Stokes drift effect?
no. Even the Stokes drift is of the order of AK square. But what I want to say is that, as I said earlier, like Ursel, for example, he predicted a mean flow in this rotating frame, which was given by and this mean flow was supposed to be the negative of the Stokes drift. So that is also an induced mean flow due to the effect of rotation. So you can have Stokes drift and also the effect of rotation. The effect of rotation on these propagating waves is to induce a mean flow, and this mean flow also is of the order of AK squared. So it can be both actually.
Okay.
At the dominant order, we have the waves and the amplitude is given by AK, and the mean flow is too weak to modify these waves. And at the next order, we have a mean flow that arrives at the second order in AK, so it's AK square. And the other thing that we take is that the mean flow varies much slower than the wave field, as in the typical time scales of the mean flow is much larger than the typical time scale of these waves. So waves oscillate at a particular time frame, let's say, and the mean flow oscillates at a much larger time scale. For example, the Stokes drift, for example, it's constant. It's just a constant drift that exists, and there's no time dependence here. And Ursel's solution also is something which is constant in time, but we'll find that actually this mean flow is not necessarily constant. Okay, so this is a description that we'll take. To understand the evolution of this mean flow, we'll look into the Craig-Leibovich equations, and these are also called wave averaged equation. Craig-Leibovich, because Craig and Leibovich derived this equation to understand Langmuir circulations, and we also call it wave average because we do some averaging process that I'll explain now. So the flow which we are considering is an incompressible fluid. So we just have to use Navier-Stokes equation with the continuity condition, incompressibility condition, which is what I did, which is what I wrote down here, and the flow is also in a rotating frame, so you also have the Coriolis effect. Okay, so that is the U cross F term that is present there. So you also have to be careful with the boundary conditions. So first is the pressure continuity at the interface. So we say that pressure at the interface is given by the atmospheric pressure. And second boundary condition is the kinematic boundary condition. So the kinematic boundary condition basically tells that the particle just sticks to the fluid, sticks to the interface, and you have an equation for the evolution of the interface and its relation with the vertical velocity W. This again is given at the interface. That is the second boundary condition. And the final boundary condition, because you have viscosity, you need one more boundary condition, which is the stress boundary condition. So we say that we are only interested in this problem without the effect of any wind. So in ocean, you can say that you can have wind at many places. You might not have wind at many places. So in the oceanic system, it's not very easy to tell what is the effect of stress per se at the interface. So we are taking a simpler system where we just say that we are not considering any wind. We just have waves that are propagating. So we say that the surface stress at the interface is zero. So there's no external forcing from the wind on the system. So here I didn't mention eta is the surface elevation, and again there's no external wind stress. So we have to now derive the equation for the mean flow. So we first expand the equation in terms of the small slope limit. So I write my velocity field in terms of AK times the velocity field associated with the waves, and AK squared times the velocity field associated with the mean flow. And I take, so we have some physical parameters. For example, the viscosity is 10 to the power minus 6 meters square per second. So which I take to be second order in AK. And the rotation is also rotation of the Earth. As I said, it's quite small compared to the typical time scale variation of these waves. So F, for example, is of the order of 10 to the power minus 4. So this again, we can take it to be a second order in AK. And at the lowest order, so if you put these values, if you put the scaling, if you put this equation into the Navier-Stokes equation and the boundary conditions at the lowest order, you get linear waves. So this, I'm sure everyone of you would have done in while you are studying, so or while you're teaching now. you have the dispersion relation of surface gravity waves, and the velocity field of the wave can be written as a gradient of a potential. Because you don't have any effect of viscosity, vorticity is 0. So this is the linear surface gravity waves. And now the question is, how do you get the equation for the mean flow? So now we do some averaging process to find the evolution equation for As I said, we take the mean flow to have an evolution which is much slower than the evolution of the wave. So we are okay to do some averaging over the faster time scale to get the equation for the slower time scale.
Just a second. It should have been omega square, right? In the last slide, where you have the arrow.
Yeah, I mean, I think omega, I'll use it for something else. So I just wanted to use C actually. Yeah, it's unfortunate.
So C square equals G by K. Yeah.
No, like omega. I mean, I just changed the notation. Omega C for me. So that is what.
Okay.
But that because like omega I'm using for vorticity later on.
Oh,
so
okay.
I could not
Okay. This, so C is the frequency of the wave.
Yeah. It's the angular frequency of the
wave.
Okay. Yeah. Thanks for the question. So now we do this averaging process over one period to find the equation for the mean flow. So if you have to do the expansion, and I will skip some steps because I don't want to do the derivation step by step. So, but just take it from me that if you do it and do the averaging, this is the equation for the mean flow that you get. It's also similar to what Craig and which did in their article. In their article, did not have the effect of rotation, but here there's an effect of rotation here. And here you see that you have an evolution equation for the mean flow. And you have an equation which looks very similar to the Navier-Stokes equation, except that here, for example, you have a extra term, which is US. So there's an effect of the wave that comes into the evolution equation for the mean flow, and this US is nothing but the Stokes drift velocity field. So it has an expression. You can write down the expression here. If you can go, once you know UW, you can exactly calculate what is the velocity associated with the Stokes drift. And as I said before, that I will show this a pictorial representation of the Stokes drift. So this one I took from Wietzer's page. So he has this nice description of Stokes drift. So let's say we have this wave that is propagating towards the right. You have a velocity field that is given by this gradient of a potential. So what happens is that if you put any particle, because the velocity field is oscillating and you have this exponential dependence along the z direction, the particle moves slightly more forward because it's on the top part of this motion. It moves slightly more forward than when it goes back, because when it goes back, it is slightly on the higher depth, and at the higher depth, the velocity amplitudes are lower. So on an average, you have this drift of the particle associated with this wave field. So this this average drift is what is captured by this US term, which is what is called as the Stokes drift velocity. So this is the evolution equation for the mean flow, and it's very similar to the Navier-Stokes equation in the rotating frame, except that you have this plus US term here, which kind of modifies everything actually, as we'll see next. So another thing that one should not forget is the effect of boundary conditions. So one should be very careful how one deals with the boundary conditions. So first, you have the kinematic boundary condition, which is also which is what leads to this no penetration boundary condition. So what you do is like you have to expand everything in terms of AK, and you do the averaging, and you do some simplification. You substitute the expressions for the velocity field and stuff. So if you do that, what one gets is that the average vertical velocity of the mean flow at the mean interface, which is z equal to 0, this will be equal to 0. So it basically means that the mean flow velocity at the mean surface, which is z equal to 0, is actually 0. So this kind of makes sense because it is very similar to the no penetration boundary condition. You do not expect it to like move up the surface, the sea level. You do not expect to move up and down. So this boundary condition makes total sense, and also you can also do it mathematically and convince yourself. So the vertical velocity on the mean surface is 0. So that is the first boundary condition. And the second boundary condition is slightly less trivial. So one has to take the stress boundary condition and expand it in terms of in orders of AK. And then you have to write down the expression for the stress tensor, expand it in terms of AK, and you do some averaging later on. And what one finds is that if you do this averaging, the actual boundary condition for the mean flow is that there is a stress that is applied by the wave on the mean flow. So this is what you get when you do this averaging process. So on an average, you do have a stress induced on the mean flow by the surface gravity waves. And this you can simplify, which basically says that the vertical derivative of the velocity, the mean flow velocity field, is equal to the vertical derivative of the Stokes drift velocity. Okay, so this is what you get when you do this averaging and this expansion in terms of AK. And I'll just stress a bit on the surface stress boundary condition because it's not very trivial. So one way to think about this is that waves actually transmit their momentum to the mean flow via the surface stresses. So you have a surface stress which is being induced by the wave on top of the mean flow, and this surface stress is actually a transfer of momentum from the wave to the mean flow. And actually, surprisingly, many studies have neglected this boundary condition due to various reasons, which I won't go into detail. But it has actually been in the literature for us from the time of Longuet-Higgins, where they also did a nice boundary layer development, and they found this stress boundary condition, and later on other people also have used it. Okay, so so this is the summary of my governing equation. You have an equation for the mean flow, governing equation for the mean flow, and you have the boundary conditions. So at the surface, as I said, there's no penetration boundary condition. You have a stress condition, the boundary at z equal to 0. And at the bottom, as I said, it's a deep water limit. The vertical velocity goes to 0. You can either take the velocity goes to 0 or the derivative velocity, or you can put some stress-free boundary condition. Actually, it doesn't matter if you take deep water limit. Everything goes to 0. So these are the boundary conditions that we will take. So the equation looks very similar to Navier-Stokes equation in rotating frame, except for the Stokes-Coriolis term. So you have an extra term here, so which is this US term that, as I was saying, and there's this US cross F term, which is actually which is totally not related to the velocity field. Right, omega is the vorticity of the velocity of the mean flow velocity field. So omega m is the curl of um, so it's related to u. But US cross F, for example, is totally not related to the velocity field. So it's like an external forcing. And this is what I'm referring to as the Stokes-Coriolis term. You have an external forcing in the system, and this acts like a body force on the mean flow. So it kind of drives a flow in the system, and actually it has some very interesting properties. This is again another term where you have rotation acting on these waves. They transfer some momentum from the waves to the mean flow. And Hasselmann actually studied a lot about this term and the consequences of this term. And actually, there's an interesting phenomena of quasi-inertial waves that are being driven by this effect of rotation on the waves. So you have some kind of a frequency quasi-inertial wave which is in the bulk of the system. So you have a mean flow which is actually driven by these waves, and it oscillates at a frequency f. So if you need more, you can go. If you need more information about this, you can obviously go and read about it in Hasselmann's work. But I won't talk much about this quasi-inertial waves. So we can solve this equation, this equation for the mean flow, and it's not very difficult. You can just look for steady solutions, and you get a laminar steady solution with the effect of viscosity. And I'll write it in terms of non-dimensional numbers. You have an Ekman number, which is the ratio of viscosity over the Coriolis term. Rossby number, again, the effect of the Coriolis term. The effect of the non-linear term over the Coriolis term. So you have these two non-dimensional numbers, and you can solve this equation. You can write down the velocity field. And actually, this looks a bit, it looks like unnecessarily long, but actually it's just composed of two parts. One is the Ekman spiral. So you have some kind of an Ekman spiral, which is being present close to the boundary, which is not surprising because we are studying flow. We are studying a flow in a rotating frame. And yeah, so if you have a question, yeah, just stop me. And the second part the first part with this exponential times Rossby and times cos and sine function, this is the Ekman spiral part. And the second part is basically the anti-Stokes flow. So we do get back so in the limit, we do get back Ursell's solution, but maybe I forgot to mention that Ursell in the study, he did not consider any effect of viscosity. So if you remember my initial slide, Ursell just took a partial T plus this equal to 0. Ursell did not consider any effect of viscosity, and obviously there was no effect of boundary condition also, because there's no effect of the viscosity was removed. So that was an Eulerian study. He used Euler's equation to study this. So here there's a difference which comes from the viscosity, which is what we'll study later on. And already from the base flow itself, you do have a system which has two components. One is the Ekman spiral, another one is the anti-Stokes flow. And just to trace the typical velocity profile, I just show some typical velocity profile as a function of the depth, which is normalized with the wavelength lambda. So as you can see, you have a boundary layer which is of the order of root of the Ekman layer. It's a root of Ekman, so this is the Ekman layer associated with this Ekman spiral. And you have another typical length scale, which is basically the length scale lambda. So you have lambda over 4 pi, which is the Stokes depth, which is another length scale in the system, and another one which is much more smaller, which is the Ekman layer. So this is a typical velocity profile at these parameters. And as I said, you have two length scales. One is the viscous length scale, which is lambda root of Ekman. Another one is the depth, which is Stokes depth, which is lambda over 4 pi. And this mean flow velocity profile is actually independent of x and y. So there's no dependence. There's no dependence of x and y in this equation. It's actually a constant independent of x and y solution. Okay. And if we take the limit Ekman going to 0, which is basically viscosity going to 0, which is actually the case in the ocean, you do get the velocity field. Actually, I should have put so the mean Eulerian flow actually goes to minus US. So you do get this anti-Stokes flow in the limit Ekman going to 0. So Ursell seems to be correct here. But there is an instability that occurs, and if you just take this flow and then look at some linear perturbations, so because of invariance in x and y direction, you can decompose it in Fourier modes along x and y direction. So this is what I do here. You have this base flow, you have this base profile, and then you have some perturbation. You look at the growth of these perturbations, and these wave numbers kx and ky denote the wavelength of these perturbations, and you have a gamma which shows the time dependence of this perturbation, and if the minus of the imaginary part of gamma is the growth rate. So if this is positive, then you have a growing unstable solution. If it minus imaginary part of gamma is negative, then you have a decaying solution, so everything is fine. So we look at the linear instability of such systems, and what we find is that actually the system becomes unstable. So here I showed this instability threshold. So I have the critical velocity number as a function of Ekman number. So we are looking at the instability threshold. So this is loss B as a function of Ekman. So we are just asking when is the this anti-Stokes flow along with this along with this Ekman layer, when is it unstable? And we find that above this curve, this blue curve, you have an unstable solution. Below it, you have a stable solution. And this is as a function of the Ekman number, and the critical values of the wave number of this instability are given here. So kx and ky are the typical wavelengths of this instability. Anyway, I won't go too much into the second graph. So here, what we find is that for loss P get done, this critical loss P is unstable, and the threshold loss P numbers are typically of the order 1. And you get two asymptotic limits in Ekman. One at large Ekman, another one is at low Ekman. And the low Ekman limit is what we are interested in, because the ocean parameters are somewhere here, like they're in the low Ekman limit. So they are definitely less than Ekman 1, so they're in the low Ekman limit, and we are interested in the low Ekman limit. So we can do some analytical work also. You do some matched asymptotics, and then you get some critical loss P number in the low Ekman limit to be 0.23. And the critical wave number of the instability is actually only dependent on x, which is interesting. It just varies along the x direction. There's no variation along the y direction. And this is actually how verification is isolating solution. And the frequency, if you remember, is very close to 1, and it kind of reminds you of the quasi-inertial wave, right? So quasi-inertial wave also has a frequency which is close to f. So it kind of points to a direction maybe that this is a quasi-inertial wave which became unstable in this system. But again, we didn't go too much into that particular direction, but just to mention this point. So the perturbation is in the x direction. And if you substitute kx to be some 2 pi over lambda x, where lambda x is the typical variation, we find that lambda x is about half of lambda. So the perturbation is of the typical perturbation wavelength is half the wavelength of the wave. So, so here I showed some typical form of the solution. So this is the unstable mode. So I show some typical form of the unstable modes, and these are some Bessel functions. And a typical vertical variation is actually of the order lambda. So it's not an instability which is driven in the boundary layer. It's actually an instability in the bulk, because it's the typical variation is of the order lambda. Okay, and you can visualize this instability also. So here I show this dependence along x, y, z direction. So I just remind you that the waves are propagating along the x direction. So they're moving from 0, let's say, to 1. So they're moving to the right. And you have an instability which of the mean flow. So initially you drive a mean flow which is opposite. So it's opposite. It's going against the wave with the propagating waves. But this again becomes unstable, and then you start forming these cellular structures, which this time are oriented perpendicular to the direction of propagation. So this is the low Ekman limit. The large Ekman limit, even though it's not very useful in the physical sense, meaning in the ocean, we do not care about the large Ekman limit, but mathematically, the solutions, the equations reduce to the standard Ekman instability. So again, this I remind you that if you take a tank of water and you start rotating the bottom plate, say, you start forming this Ekman layer near the bottom plate, and this Ekman layer again can become destabilized at above some critical Reynolds number. And this was studied by Fowler in the 1960s, and yeah, you can go and read about it. But at large Ekman limit, as I said, is not very interesting for us, so we do not consider this limit. Okay, so what are the physical implications of this instability that we found? So as Professor Mahendra Verma was asking, what are the typical values that you get in the ocean? So typical values of surface gravity waves, at least the swell waves, the typical wavelengths are of the order of, so swell waves we take because these are the waves which are like monochromatic and they travel for very long distance. So analysis works very well for them. So typical wavelengths are of the order of 40 meters to about a kilometer, the longest, the very, very large wavelengths. And typical wave heights can be of the order of meter to about 10 meters. And Stokes velocity field, we get velocities of the order of 0.01 to 1 meter per second. And if you substitute these values, take the viscosity, this gives us Ekman numbers of the order of 10 to the power minus 7, and the numbers of the order of 1 to 10. Okay, and so basically what we find is that it's very much higher than Rossby critical, which I remind you is of the order of 0.2. So we do get an unstable mean flow. So going back to the picture presented by Ursel, you have a flow which is driven, which is opposite to the direction of propagation, which we call it the anti-Stokes flow. And what we say is that this anti-Stokes flow, even though it's established, actually gets destabilized. And second question that I wanted to ask was this effect, the dissipation of this mean flow. So how much does this mean flow dissipate? How much energy does the mean flow extract from these waves? So that is the second question that I wanted to ask, and or maybe the first question. Maybe the first question. What are the? So how can we say something about the dissipation of this mean flow? We used a method which was quite successful here, which need not work all the time. So this method which we used, the method of bounds. So what we did is we took the equation for the evolution equation for the mean flow, and then we took the dot product with plus us, which is the Lagrangian velocity field, which is the mean flow plus the Stokes velocity field. So plus us is also called the Lagrangian velocity. So it's the sum of Eulerian velocity field plus the Stokes. So we took the dot product with plus us, or dot product with the Lagrangian velocity field, And what we found was that the nonlinear term totally disappears, and you get an equation of this form. And what you can do is, like, now you can analyze this. You can take the average in time, and then you take the average in space. So if we do this particular process, what we find is that the dissipation of the mean flow, which is defined as P dis, which is nothing but the rho nu over Lx Ly integrated over the domain of gradient of u whole square dx. So this is a dissipation rate, which is equal. So this you can find the other terms in the equation, and what you find is that you have a first term which is proportional to nu us square, where I remind you us is the velocity, the amplitude of the Stokes drift, k is the 2 pi over lambda, and rho is the density. So you have one term which is of this form, and the second term which is related to the average of over the domain with similar coefficients, where again you have viscosity. So finally, we get the dissipation rate to be much less than the dissipation rate of the waves. So you can again compute the dissipation of the rate of the waves of the order of nu k square. So it's the dissipation rate of the mean flow is very much less than dissipation rate of the, it's less than dissipation rate of the waves times a factor which is ak squared plus a fluid number. So ak squared again is the slope of the wave. This is what you get by analyzing these terms, and you get a fluid number which is nothing but the maximum velocity of this mean Eulerian flow over the velocity of the propagating wave. So the phase velocity of the propagating wave. So you get a fluid number here, which again is something which is of the order of ak square. So both of these terms are of the order of ak square, and as I mentioned before, ak is the small parameter, so which basically means that the dissipation rate of the mean flow is actually very much less than the dissipation rate of these waves. So what we find is that the dissipation of the mean flow is very similar to the dissipation rate of a typical laminar flow, meaning firstly you have a coefficient which is proportional to viscosity, and it's actually much less than the dissipation rate of the wave. So what it implies is that the mean flow, even though it becomes destabilized, and we'll show later that actually it can become turbulent, even though it becomes destabilized and turbulent, it's actually bounded by the viscosity firstly, and secondly, it's very much less than the dissipation rate of the wave. So the mean flow does not extract much energy from the waves. Okay, so this was one of our conclusions. And the second question that I wanted to ask was this importance of this mean flow and this destabilization on particle transport and mixing. So firstly, we showed that Ursel mentioned that he found that anti-Stokes flow is what we get. So where I wrote UL is again UM plus US, and Ursel showed that UM is equal to minus US. So this should be close. This is equal to 0 according to Ursel. So there's no mean Lagrangian velocity transporting particles. So according to Ursel, the transport properties are. But the anti-Stokes flow can become turbulent for Rossby's much greater than Rossby critical. This is what we'll show later on. And so now we can use some phenomenological arguments from turbulence. Now the question is whether the dissipation rate, which is the turbulent dissipation rate, is U cube over L. So this is proportional to the injection rate. So this is the phenomenological turbulence argument. We say the dissipation is given by U cube over L. But the dissipation rate here, I just showed that it's less than the dissipation. It's bounded by the viscosity. So this should be less than or equal to nu US square by L square. So this is what we find from the bounding theory, that the dissipation rate is less than something which is bounded by the viscosity. So this basically implies that the velocity, the mean velocity field that we get, the Eulerian velocity field that we get over the velocity of the Stokes drift is of the order of Ekman to the power 1/3. So this is because you have viscosity here, so there's an Ekman here. But the question is, should one use UM or UL? And what can we eventually say about the mixing property? Does UL actually go to 0, or is it non-zero? Like, is UM going to 0 or is UL going to 0? So that is a question that was not very clear. Should one use the mean velocity field, the mean Eulerian velocity field for this problem, or should one use the mean Eulerian velocity field plus the Stokes drift to understand the mean flow, or to understand the transport properties or the turbulent properties of this system? Okay, so we did do some nonlinear simulations. So these are some work which I did more recently, And we used a code called Daedalus, which is an open source code. Firstly, we checked with the theory that with the theoretical argument that we do predict a growth and a decay whenever the system is allowing for growth and decay using this linear stability analysis. And secondly, what we found is that the unstable mean flow, the case when it becomes unstable, it actually becomes turbulent. So, can we now, using these nonlinear simulations, can we say something about the low Ekman limit? So we did more extensive studies. So what we did was we took a simple setup along X, Y, Z directions, where Lx, Ly, Lz are typical length scales, which are typically associated with this box domain. And in order to have a system which is independent of the box size, we took Lx, Ly, Lz to be of the order of lambda, or a few times larger than lambda, so that all variations are less than lambda, and we do not miss out any large-scale variation. And we applied proper boundary conditions, test boundary conditions, test-free boundary condition at the bottom, periodic boundary conditions along X and Y direction. And here I show some typical snapshots. So here's in the XY plane. No, this is the XY plane. This is the XZ plane. So you have some vertical structures. So the lines show the velocity field, and the color bar shows some amplitude of the velocity field. So you have some nice structures that are getting formed. And from the visualization, we do see that it looks a bit turbulent actually. Okay. So what happens in the limit? Ekman goes to 0. So as I said, by using phenomenological arguments, you say that U cube over L should scale like epsilon. And the question is, which U should you take? Should you take UM or should you take UL? And whether does UL go to 0 or does UM go to 0? Because even though UM is equal to minus US according to Ursel, we do find that it's unstable and it becomes turbulent. And according to turbulence, either you say that UM, or if you take UM velocity field, U cube over L scales like the dissipation rate. And since the dissipation rate is bounded by viscosity, U goes to 0 as viscosity goes to 0. Or you can take U to be UL, where you say that UL is bounded by viscosity and UL goes to 0 as viscosity goes to 0. So this is what we'll be verifying here. And what we find is that in the limit of low Ekman, it's Rossby number, we keep it fixed. What we find is that here I show the Eulerian component. This is UM, sorry, I didn't write M here, subscript. So this is the Eulerian energy and this is the Lagrangian energy. And what we see is that in the low Ekman limit, U goes to U square over US square goes to a constant, whereas UL square over US square scales like Ekman to the power 2/3. So this kind of shows that the Lagrangian velocity field follows the predicted scaling from phenomenological arguments, where you say that U cube over L is proportional to epsilon, and since epsilon is bounded by viscosity, U square scales like Ekman to the power 2/3. And this is what we find here. So the Lagrangian velocity field follows the predicted scaling, and in order to understand whether does it have any implication for the transport properties, we do find that U square over US square goes to 1, meaning that U square is proportional to US square, or like UM, which is the Lagrangian velocity, which is the Eulerian velocity field, is of the order of US. So you do get an anti-Stokes flow in the system, even though it's turbulent. But the Lagrangian velocity field, which is UM plus US, actually goes to 0 in the low Ekman limit. So we do get back to Ursel's prediction of of an anti-Stokes flow, just that it's highly turbulent, and it is turbulent and it is fluctuating. And actually, we do have a deviation from. So since it's a fluctuating quantity, we do have some deviation in space, and particularly if you take the surface velocity field. Here I show the typical averaged value of the Lagrangian velocity field at the surface, and along the x direction and the y direction, we do find that in the limit of Ekman tending to 0, we recover the Ursel solution. But for moderate values of Ekman 10 to the power minus 5, which is also typical of the ocean parameters, the deviation from the Ursel solution is actually not negligible. So it can go up to order 0.3, like 30% from the solution of Ursel's anti-Stokes flow. And if you take So if you take a turbulent viscosity, which is Ekman, many people say you can take 10 to the power minus 4, 10 to the power minus 3, which is what people use in modeling. In ocean systems, if you take a turbulent viscosity, then Ekman numbers are much higher, so you get much higher deviation from the anti-Stokes flow. So in terms of implications for particle transport, we do find that even though the system goes to the anti-Stokes flow limit, there is a significant deviation if you look at the spatial structure of the system. So with that, I conclude my talk. So surface waves transfer part of the momentum to the underlying mean flow. And this wave averaged equation, it predicts a time-independent mean flow, which is unstable, and this unstable mean flow becomes turbulent. This we just showed by doing some numerical simulations. And the dissipation rate of the mean flow is actually much lower than the dissipation rate of the wave because it's bounded by viscosity. And if you write it more carefully, it's actually bounded by the dissipation rate of the wave times some parameter which is AK square. So it's much less than the dissipation rate of the wave. So in conclusion, it does not take much energy from the wave. But in terms of particle transport and mixing, we do find a strong deviation from the anti-Stokes flow, even though in the very low Ekman limit, one does expect to get the anti-Stokes flow. Because of the finite value of viscosity, you do see a deviation from the anti-Stokes limit. So some open questions from this particular subject. So realistic ocean, for example, has a very unsteady waves. So we took a very generalized system where you have this monochromatic waves that are propagating from one direction to another direction, from one place to another place. But in real ocean, you have very fluctuating wave field. So you have unsteady waves. So how does an unsteady Stokes flow modify the resulting mean flow? So this was recently studied by this person Higgins at Oxford, and they looked at certain questions about it, at least the laminar part of it. And the question is like, does the turbulent field change a lot? So does it affect the turbulent flow? Does it affect the scaling of the Lagrangian velocity field and its mixing properties? So these are open questions. And turbulent viscosity, for example, so what people take in the ocean is that you have like perturbations at much smaller scales, and people say that one should model this with the turbulent viscosity and not a simple laminar kinematic viscosity of water. So you should take a turbulent viscosity in these systems, and if you take that, you do get large deviations from the anti-Stokes flow. So what is the typical value that one should take for the upper ocean? Like, should we be worried? Should we really consider the effect of this this turbulent viscosity, like how sensitive it is to the value that we take? And in the broader context, maybe this mean flow, which maybe the waves themselves, even though people thought did not transfer a lot of, they're not involved in a lot of particle mixing, but this study shows that the underlying mean flow also plays an important role. And even the waves themselves might not, people are not looking at them, maybe the whole system of wave plus mean flow system actually transports a lot of particles. And finally, what does the effect of stratification? Even though we are looking at the upper ocean, which we don't expect it to be very stratified, in some places we do have a strong effect of stratification, and the question is how can stratification affect all the study that we did, and this remains an open question. So with that, I thank you for your attention. So if you have any questions, I'll be happy to take it. So here's a nice visualization of Langmuir cells, which where you see this upwelling, which is what you see as these lines, and these are waves that are propagating along the direction. Anyway, so if you have any questions.
Okay, thanks, Kana, for the nice talk.